For question 7, the table gives information about the times taken in seconds by the athletes in the 5,000 meter Diamond League race held in Oslo in 2016. And we're given a table with our 20th percentile, our median, and our 80th percentile. The cumulative frequency graph shows information about times taken in seconds by the 18 athletes in the 5,000 meter Diamond League race held in Zurich in 2016 as well. And then there we go, we've got our cumulative frequency diagram. So, part A asks us to use statistical calculations to determine in which of the two races the times taken by the athletes were the least, and in which of the two races were the times taken by the athletes more consistent. You must explain how you reach your conclusions. Okay, looking at the first thing is the marks. The number of marks is 5. So we're going to have to make 5 important parts, not in 5 points necessarily. It says here using statistical calculations. Now that's an important thing because it means we're going to have to use some numbers somewhere. This and is important because it means you don't choose one of the points, you need to do both points. And the points are, we need to determine which of Oslo or Zurich, which I'll just refer to as the different races, which one was the least in general, and which one was more consistent. So that's basically our main points. We need to use statistical calculations to do those 2 points. So it might actually be useful for me to explain what this actually means. Percentiles. Now percentiles might look a bit daunting at first, but it basically holds the same principles as the lower quartile and the upper quartile, which we explored previously in the other question. We know that the lower quartile represents everything from 0, or it represents the 25th percent value of the data, and the upper quartile represents the 75th percent of the data. And for the same thing, the median is obviously the middle of the data, or 50% of the way. Now you can apply the same principle and you see that the 20th percentile is 20% of the way through the data, and the 80th percentile, you guessed it, is going to be 80% of the way through the data. And that leads us to another thing, where we had the IQR, which was short for interquartile range. We now actually have something called the interpercentile range, which instead of using quartiles, which was the lower quartile, the upper quartile, and the median every 25% or quarterly, we're doing percentage. We're going to the 1%, and therefore it's called interpercentile range. So the interpercentile range is not specific like the interquartile range. The interquartile range is always the upper quartile minus the lower quartile, or 75 minus 25%. The nice thing about interpercentile range, well, it's usually typically around the 10 to 20 and 80 to 90 points. You can use any two percentages really. And here we've got our 80 and our 20 percentile. So it makes sense if you're going to compare this data, which is for Oslo 2016 to Zurich in 2016. If we're going to compare those two, then you might as well use the same format. And the format is, they've given for the first one is the median and the 20th and the 80th percentiles. Now with the median, we can just compare it just as we did with our box plot question, compare those two. And as you saw, we compared the IQR for the box plot questions. It's a bit similar here. We're just going to apply the same thing and find the interpercentile range this time and compare the two. Now, looking at a cumulative frequency diagram, how do you find the median? Because first of all, you might as well look at that. We know that the median is half of n, or half of n plus 1 if you're looking at discrete, but since we're looking at a cumulative frequency, it's continuous data we're looking at, so we're going to do half of n. Now, if you zoom in closely, you can see that each box within here represents 0.5. You can see this goes up 10 squares and it represents a distance of 5. So yeah, each box represents 0.5. And if you count downwards from 20 and 0.5, you kind of see that this is actually 18. The maximum value is 18. So we're going from 0 all the way up to 18. And halfway through that value is going to be 9, which is going to be roughly somewhere here. Now, if we do that, we draw a ruler at this point and we basically mark off. So 9 can be found 2 squares below 10, as each one is an increment of 0.5, and you just join them together. Now we see where that hits. and we roughly get around, and you can see that the points here go up in 1, and this is kind of cutting it in half almost. So we can see that it's between 805, which is that bold point here, and then the one after that is 806. So we're looking at around 805.5 if we're being quite accurate. I'm pretty sure they'd allow you some leeway in the mark scheme if you're not too accurate, but you should be accurate. And you can see mine was slightly off here, the line, the horizontal line, so if you went a bit more higher, it would hit dead on center between 805 and 806. So that's the median value for, I think that was Zurich, the diagram one. Yeah, so that's the mean one for Zurich. Now, mean, why have I put the mean? It's actually the median. So if we look at the median of Oslo, it was 794. So let's compare 794 to 805.5. So 794, which was for Oslo, versus median of 805.5, and this one was in Zurich. And now let's directly compare them. 794 is less than 805.5, therefore Oslo was quicker or quickest, as median was lower. So we've looked at which one is the least. Now we need to look at the consistent part. Now the consistent part, if you go back to the earlier question for box plots, they're very similar. We looked at the median to compare, I think it was heights, the context was, if I'm not mistaken, and the consistency was measured with the IQR. The same applies here. We're looking at the interpercentile. We're looking, rather than the middle 50% data, we're looking at the middle chunk of data, and we can't really tell what it is, other than the specific question, of course, where we're looking at the 80th minus the 20th. So we're looking at the middle 60% of the data here. But in general, we don't really know what it actually is. So the middle 60% of the data, just like the IQR, the idea is to give a measure of the spread of data and not affected by outliers too much. So to do the 80th and the 20th percentile, well, we're going to apply the same thing. If you don't know what I did for this one, I didn't really go through it in detail for the median, but we did half of 18, which gave us our 9. So half of 18 is equal to the 9th value on the y-axis, or your cumulative frequency for the median. Now if we look at our 20th percentile, now the 20th percentile is going to be, rather than half, it's going to be 1 over 5, or 0.2 multiplied by our total frequency, which is 18. And that gives us 3.6. Now we've got to find 3.6 on this again, so it's going to be below 5. We just have to count properly what that's actually going to be. Now it's a bit annoying because the scale is in 0.5. So 3.6 is actually going to be quite annoying to find. So this is going to be 4 2 squares belief, and then this is going to be 3.5. So we're going to go just slightly over. And doing that, okay. So yeah, I've joined the line slightly to the right too much, but you can see that it's kind of hitting 2 squares to the left of 800, and that is 798. So the value of the 20th percentile, that's y-axis by the way, is 798 from what we've seen. Now we'll just apply the same for the 80th percentile. The 80th percentile is going to be 80% away through the data, or 0.8 times 18, which gives us the 14.4 value on the y-axis. So to find this, we're going to just go to 14.4 on the y-axis. Again, because it's not a multiple of 0.5, it's going to be quite annoying rather than anything else. So we've got to just really aim for as accurate as we can. and that comes up at 814. So yeah, that one wasn't too bad because it lied quite nicely. Now the mark scheme should, and I'll double check it in a minute, they should give you some leeway on the values of your IPR values, which you're going to calculate now, and it will be based off obviously the readings you get here. So if you're not 100% accurate, I wouldn't say don't worry, but hopefully you shouldn't worry too much in the exam. Just know that they do take into account human error. So to find the interpercentile range, we'll just do the value of the 80th, like the upper quartile essentially, minus the 20th, or the lower quartile in the other example. And then we'll just do 814 minus 798, type that into your calculator, and we get 16. So we'll just write that here. So the interpercentile range, and it'll be useful to mention that this one was for Zurich since we did the graph rather than the table. Was 16. It might be helpful now to look at the interpercentile range of the table, or Oslo. We have 808 as the 80th, 789. Now using the same method, the 80th minus the 20th, I'm just going to put them into the calculator, and I get 19. So I'm going to put that into the answer. So whereas for Oslo, now just for as the IQR measured the middle 50% of the data, the interpercentile range works similarly to do a different proportion, but still the middle data, which should hopefully make it free from outliers. And the whole point of that is to measure consistency. So consistency, if you see a lower value, that's going to be the more consistent one. Here that was Zurich. To highlight where the marks came from, you would get 1 mark from actually finding the median, and then 1 mark from actually doing the comparison. So finding that Oslo was the quickest, and that would give you 2 marks. You then also get 2 marks from finding the interpercentile range for Zurich, and the interpercentile range for Oslo. That's another 2 marks, and then you get your last mark from obviously the context, stating that Zurich was more consistent. And by doing this, we've addressed the statistical calculations, the least values, and the most consistent values, and that's the 5 marks achieved. And yeah, you might think, well, it's not easy to think about it straight off the bat in the exam. You're just going to have to practice loads of questions and just brain dump. If you want to leave this for the last question, if you just want to go ahead, there's no shame in doing so, because sometimes you just need to leave the hardest questions till the end. I'd say this is what separates a grade 8 to a grade 9, because interpercentile range isn't typically taught that much. It's not emphasized on so much because it's just not covered that much in exam content. So if it comes up and you know this, well, you've got a heavy advantage over other students. The interquartile range of the race time in Zurich is 13 seconds. The greatest time taken by an athlete in the 5,000 meter race in Zurich is 840 seconds. Mo thinks that this time is an outlier. Determine whether or not Mo is correct. Now, there's 2 types of outliers you learn in statistics. The one is that we've actually used quite a bit is 1 plus or minus 2 standard deviations. Now this is for sample data. But when we're talking in context of IQRs and upper quartiles and lower quartiles, we have another formula for the outlier, which is the upper quartile plus 1.5 IQR and the lower quartile minus 1.5 IQR. If you want to visualize this, we have our lower quartile here, your upper quartile here, and then your IQRs are like this arrow and this arrow. Now, if your data falls outside this dotted line here and this dotted line, then you can say everything outside in this region and this region is safely an outlier because it's past the lower quartile minus 1.5 and upper quartile plus 1.5 of the IQR. So which one do we need to use? Well, he thinks the greatest time taken by an athlete is an outlier. Now, the question is that going to be the upper quartile or the lower quartile? 840 seconds on the graph. 840 is here. And if you trace it upwards, you can quite clearly see that this is at the top of the cumulative frequency graph. So by definition, it's not going to be in the lower quartile of the data, is it? It's going to be at the top of the data. Dare I say it, it's going to be near the greatest value of the data. So to do an outlier test, we're going to use the top equation here. We're going to use the upper quartile plus 1.5 of the IQR. Now, if we do this, we need to find the upper quartile. The upper quartile is the 75th percent of data. Go into your calculator and do 18 times 0.75, which is the equivalent of finding 75% way of the data, and we get 13.5. We need to find that here. Luckily, it fits to the scale. Right, so we get a value close to around 812.5-ish. I kind of drew the line off again because of the pen ink. It's kind of, you can see that it's not quite hitting the line, so it should be a bit more to the right. And looking at this value right now, it's bang on 812. So to compensate for that, I'd say it's 812.5, and that's what it says in the mark scheme. And also, just to verify, the mark scheme also accounts for what I just did there now, saying 812. It says anything which rounds to 800 and whatever the answer will be soon. The idea is they choose values, and if you're slightly off, let's say you chose 812 here instead of the value I'm going to do now, the calculation should get you close to the final answer, which means you should hopefully get the full marks. Anyways, so we need to look at the last one. We just need to substitute our value for the upper quartile, which we now know to be 812.5. We need to add 1.5 lots of the IQR. The IQR is going to be 812.5 minus something, but we don't know what that is yet because we haven't found the lower quartile. So let's find the lower quartile. The lower quartile is going to be 25% of the way through. So 25% of 18 is 4.5. So we're going to find 4.5. And let's do that quickly here. Again, it's around halfway through that little square, so it's going to be a point something. So looking at that just by eye is 799.5. I'm going to quickly type this into the calculator. 812.5 minus 799.5, and we get 13. So we need 1.5 lots of the IQR, which is 13. I'm going to type this into the calculator now. And you get 832. That's the final answer. Now, as I said, the mark scheme says anything which rounds to 832. So 832 is the limit for an outlier. And Mo thinks that 840 is an outlier. Well, is he correct? Well, yes, he is, because 840 seconds must be greater than our bound of 832. If you think about it, the cutoff is here, and this is 832, and the data is here, 840. So it's outside the region for which it should not be an outlier. So it is an outlier, therefore Mo is correct. Just want to add now quickly that if you have any ideas or videos that you want me to make, be sure to leave them in the comments below. Owen collected data about the number of people per kilometre squared living in each of the 56 counties of England and Wales in 2015. Some information about Owen's data is shown in this incomplete table. So this is a grouped frequency table, as we have our class intervals here and our corresponding frequencies here. The number of counties that have at least 600 people per kilometre squared. Now we just need to use the number of people's column, which is this one here, and we need to find it where it's greater than or equal to 600 because of the at least 600. At least 600 means 600 inclusive. If it says more than 600, you typically assume this to be 601, 602, for example. That's just something useful for all exams. So that's these two columns here, because as you can see, this is 600 to 1000, and this is 1000 to 6000, and they are all greater than 600. So R plus S, well, we don't really know what R plus S is, but we're given another key piece of information here, 56 counties. Now, you should know that in a group frequency table, all of these values here should sum, and they should sum to give 56 because the total number is 56 counties. So we know all of this is equal to 56. So we can formulate an equation, and you could say that 15 plus 14 plus 14 plus R plus S equals 56. Since we're only interested in R and S, we'll basically just rearrange for R and S. And doing so, we get R and S, which is 13. And since R and S is greater than 600, this will just be our final answer. Part B. Use linear interpolation and the information in the table to find an estimate of the median number of people per kilometre squared. So the two key words, estimate and median. So we need to use linear interpolation. It's just a fancy term for finding the median. Now for continuous data, we typically use half of n. Now if you use half of n plus 1, it doesn't really matter. The mark scheme does account for that answer too. So half of n, what is n here? 56, because that's our total. So we can say that half of 56, which gives us 28. We want to find the 28th frequency or the 28th value. So the next step is looking at which row this is in. So if we look at the frequency here and we make our own cumulative frequency table, probably should be doing it on the right, but I'm going to have to do it on the left. So it's 15 when it's between this interval. When it's less than 400 as well, it goes up to 29. I'm just adding the 14, and then I add this 14 and I get 30, 43, so 43. Now 28 is the value we're targeting, and 28 is clearly going to be within this row here because it's under 29. So we're trying to find the median, and we know based on the information that it's in this interval right here between 200 and 400. The question is, what value of x can we put down as our estimate? So we know that we're trying to get to the 28th value, and we know that this is a 200th to 400. Okay, so we also know that in this interval we have a total of 14. And at the start of 200, we basically have 15. And we get to 29. We want to get 28. So basically we need to represent it as a proportion. So to get from 15 to 28, we need to go 13 along. And so there we can do 13 out of the total of that interval, which is 14. And the class width is 200. Now an assumption of this, because it's an estimate, is that it's evenly spread throughout the whole interval. So we'll multiply it by 200. As you can see, 200 to 400 is a 200 gap. Now that's not all. Now we know how far into the interval we're actually going, if you visualize it. But where do we actually start? Well, we add it onto the 200. So if we kind of use it like so, we need to do 200 plus this. Now I'll type this into the calculator, and we end up with 386 to three significant figures. I mean, you can expand it first if you want more simply. And that's the final answer. Using the information in the table, explain how the mean of Owen's data would compare with the median of his data. Okay, now this is all about skew. You know that we can represent a group frequency table with a histogram. Now I'm going to do a rough plot of what this is. We have the table values of 14, 15, 14, 14, and then R and S, and we don't really know those values, but we know that it's combined 13. So the idea is, it's basically a continuous version of a bar chart. We use it for continuous data rather than discrete. And you just look at the general shape. And the general shape goes towards the right, the tail goes to the right, and that means that outlier values are positive and they're pulling it upwards. So this is obviously positive skew. Now in positive skew, you should know that the mean is greater than the median. Now I'll write that down and explain it why. So obviously now's not the time to explain it all, but when you have a little diagram, the mode is basically the highest point you hit, and this is obviously symmetrical, so the mean and the median would be here. So a better example, going back to our positive skew, well, the mode will be here because this is the peak value, and looking at the mean is going to be pulled by these extreme values, like your outliers. So for example, if we had ages, so like let's say this is 150 years old, and let's say this was 150 years old, and this is pulling the mean age up. So the mean would be somewhere around here, and the median's always in between these two or equal to it for a symmetrical distribution. So we can say that the mean is going to be greater than the median. I'd recommend that you revise it in more detail if that short explanation didn't make too much sense. Part II. Explain whether the mean or the median is the most appropriate measure of central tendency for Owen's data. Just like the example I just spoke about. Now this example was about counties, but it would probably be better for me to just stick with the age example now. Now let's say 150 years old. If that's going to pull up the mean age, well, that's not really a good representation, is it? Now let's say you're trying to see the mean age of, I have no idea, but let's say you're trying to find the mean age of something, and having 150 years might not be what you want, as it pulls the mean age up. It's basically skewing the data. So the median is going to be the most appropriate here. Owen uses statistical software to draw a histogram to show the data he collected. Explain whether or not a histogram is appropriate. Well, we already said that earlier, that a histogram is appropriate because a bar chart is used for discrete data and a histogram is used for continuous data, so you can say yes. Now you'd also get a mark if you said that they're grouped data. Owen prints his histogram, but his page gets torn. Here is what remains. Work out the values of R and the value of S in the table. Okay, this looks harder than it actually is, so I'm going to go back to the actual table. Now, the parameters for R was the intervals of 600 and 1000. So we're looking at everything bound by this part here. So the idea is we want to get the remaining area. Now, this is frequency density and the number of people. Now, this brings us on to what the frequency density actually is, and the area in here is basically the frequency. So we can find the frequency, which is what we're trying to find here, the number of counties, by just using our formula. Now, the frequency is equal to the density multiplied by the class width. So, what is the actual class width here? The class width we've found is 600 to 1000. So if we write this out, 600 to 1000, no idea what I'm writing in red here, then we can say that the class width is 400. And that makes sense. And you can kind of see that it's going to be a rectangle because if you finish this off, you get this. So we're trying to find the area of this entire shape. So we know that this is 400. So now it makes sense to find this side here. And this side is just the frequency density. Now this requires you to read off what the corresponding y-axis or the y value is. So you can see the increments here. Well, it's 0.005 for 5 squares. So one individual square would be 0.001, and half a square would be 0.0015. I know, that's quite crazy. So 0.001, let's use that as the benchmark. We need to go above 2 squares and then another half square. As you can see, this is quite intricate, but it's half a square. So we go half a square above that. So we need to do 0.01 plus 2 squares plus half a square, so just 0.0015. I've just looked back and I made a crucial error. Half a square is actually 0.0005, so these needs to be fixed there. I'll concede that, sorry for the mistake. So doing that, you put this into the calculator and we actually get 0.0125. So now we know that. We know what the frequency density is, we know what the class width is, now we can just use the formula. Or you can just find out that is the area. But the formula is something useful to know for statistics at least, because you might need to find the other variable in a different question. So we'll just do 0.0125 multiplied by 400, type it into the calculator, and we get r is equal to 5. Now you might think, how on earth am I going to use that to find s, which is presumably this part of the histogram? Well, now you can just use some common sense. If all of this adds up to 56, and now we know that this is actually 5, well, now we can just put that back into the formula. You can see that r plus s is going to equal to 13, so s must be 8. And you can show that in the calculator, or you could just write it in. It's not much workings you need for this one. And that is question 8 done. Question 9. Okay, we're moving to absolute and relative risk. Now, as statistics does have its perks, this is one of the topics that has historically been my weakness, and I don't particularly like it because it's just hard to get your mind around. That being said, I'm going to try my best. The ambulance service has a target of responding to 75% of life-threatening calls in 8 minutes or less. The table shows the actual response rates for 2 locations in the UK in 2014. For a life-threatening call made in 2014, write down the absolute risk that an ambulance takes more than 8 minutes to respond in Littlehampton. Highlight the information we've been given. Littlehampton, and we need to find the probability, or the risk, it takes more than 8 minutes. So it is a percentage, so it's a probability in that sense. So this is for 8 minutes or less. So if 75% are answered in 8 minutes or less, then 25% are done in 8 minutes or more. So 25% are done in 8 minutes or more. Now write down the absolute risk. The absolute risk means that you're just looking at that in general. You're not looking at it in comparison to another variable, another location. So you'll just be 0.25. For part II, we need to work out the relative risk that an ambulance takes more than 8 minutes to respond in York compared with the target. Now, we need to bear in mind that the target for the actual national was 75%, and Littlehampton actually met that, so that's quite a interesting thing to note. So the relative risk has a formula. It's the risk of group A over the risk of group B. Now the risk of the order you do it in does make sense, because you need to find the relative risk of York compared to the target, and the target is 75%, as we've seen here. So the relative risk of York compared to the target would be finding the risk of York itself, and the risk of taking more than 8 minutes, we've already clarified it, would be 100 minus 93, which is equal to 77%, sorry. So we know that it's going to be 7%. Now the national average was 75%, and coincidentally Littlehampton had 75% as well. So we already know that it's going to be 25% of the time it's going to take longer than 8 minutes. So if 25% of the time it takes longer than 8 minutes, and York compared to that only takes 7%, so we can say 7 over 25%, which is just 7 over 25, and that's your relative risk. And the idea is, if you think about it as it is a decimal, it is 0.28, if I'm not mistaken. So if it's 0.28, it's saying the risk of an ambulance being later than 8 minutes in York compared to the country is 0.28. Now if the relative risk was equal to 1, you'd say that they're roughly the same, like the risk is going to be the same wherever you are in the country. If it's greater than 1, then the risk in being in York of having a late ambulance is going to be higher. But because you're looking at York compared to the country and it's less than 1, it's going to be a lower risk, which makes sense because York's quite good. Look, they've got a 93% response rate. So that's the answer, 7 over 25. So you probably see what I mean by relative risk being mined. It's a concept that you need to properly understand, and I'm a bit rusty on it. I have not done it for a year, let alone when I was revising it. I always found it a bit of a daunting topic. However, don't let that deter you from doing it, because it could come up and you should know all the content regardless of how difficult you find it. So yeah.